Hello, am I audible?
Good afternoon, sir.
Good afternoon. Okay, so I guess we can start. So, welcome to the week 5 live interactive session NOC24 EE-28 Signals and Systems. Uh, as usual, the course instructors are Professor Hitesh Shimali and Professor Kushal Kesha. We go over through the guidelines, uh, while prerequisites of this session will be the last week's lectures in the course that covered the following topics: the overview of the systems and the general properties was discussed. Uh, LTI systems, they were discussed, and also the frequency response of RLC circuits was discussed in the last week's lecture. So that would be the prerequisite for today's session. And yeah, I hope all have attempted this assignment 5, okay, before the session. So let us briefly recap what we learned so far. Linear time invariant systems, right? LTI systems, the systems that are linear as well as time invariant, right? And why are these systems special? We'll uh, get to know that. Okay, consider the arbitrary discrete time signal x of n. Okay, x of n is my arbitrary signal, right? And I have some system S, right? I'm interested in the expression of y of n, right? This is my interest. So I'm sure you will know that x of n can be written as, you know, a summation of these impulses, shifted impulses. Okay, so we can write x of n by this summation in general, right? Because x of n can exist for any n. So that's why we are taking this summation from minus infinity to plus infinity. So
Sir,
yeah, please go
sir,
ahead.
here Xn is a discrete signal, sir.
Yes, this is a
Sir,
discrete time signal. So what I'm trying to do is I'm trying to develop a motivation for convolution sum in discrete time case. And from there onwards, we'll then uh, write the convolution integral on similar lines. Okay, we'll develop motivation for the convolution sum for discrete time case. That is my objective. Is that clear?
yes, sir. I have another doubt, sir.
Yeah, please go ahead.
Sir, discrete signals are also called discrete sequences, sir. Discrete sequence and discrete and sum are different things, na, sir.
Discrete, yeah, usually we write that as discrete sequence, right? The point is that the signal won't be continuous, right?
Yes, sir. Sir, the
So
sequence and the sum of sequence, these are two different things, na, sir.
sum of sequence and a sequence. Yes, if you have one particular sequence, that is a sequence. But what do you mean by sum of sequence? Uh, that would effectively mean summing the sequences, and the resulting sequence would also be a sequence, right?
So the result would be a number, sir. It would not be a sequence.
Okay, okay, I got your point. What you're saying is, okay, so maybe I got your doubt as well. See, okay, x of n is 1, 2, 3. Maybe you're confused with this part. You're saying that I'll sum over the entries, and this would be a number. 1 plus 2 plus 3 is
5.
6, right? 1
Okay,
plus 2
yes.
plus 3 is 6. So yes, that would have been the case had I written something like this: summation I, say I vary summation over I, and then xi. This would have been 6. You are right. This would have been a number. But the fact that I'm introducing n inside this summation, right? That means this will no longer be a number. Why? Let's see why that is the case. So let me instead take an example. Okay. Suppose I have x of n. Uh, Let me instead show it graphically. Suppose this is my x of n. Okay. And x of n takes the value 1. This is at n equals to 0, right?
Okay, sir.
And suppose it occurs like this. I'll make a random case. In general, it could occur from minus infinity to infinity, right? But let me take a very specific case. Suppose now we randomly fill them. So suppose this is value 2 at n equals to 1, and say this is value 1.5 at n equals to 2. Likewise, suppose it is 0 at n equals to minus 1, and it is again 2 at x equals to minus 2. So by that summation, what I mean is I can write this x of n as summation over I. It's x of I times del of n minus I. So what is, okay, let me first write this x of I del of n minus I. Right, this was that equation. Let's see why this is not a number but a sequence, since that was your doubt. This would be what is, I'll start from minus 2, right? We'll start from
Okay.
minus 2 all the way till 2. So when I is equals to minus 2, this would be x of minus 2 del of n plus 2, right?
Yes, sir.
And likewise, I'll similarly fill this up and then we'll discuss x of minus 1 times del of n plus 1, right? Similarly, this would be x of 0 times del of n plus x of 1 times del of n minus 1 plus x of 2 times del of n minus 2. Is this fine?
Okay, sir.
Okay, now since, okay, now let's see. I'll do one thing. See, this was how my x of n was defined, right? So I use these values in this equation, and now I'm asking you to plot this, right? And my claim is that this would be x of n. Why? Because see, this particular term, this would be 0 for all n except n equals to,
N is equal to 0, sir.
yeah, n equals to 0. And what would be the value at x equals to 0? See, this is unity, right? The
Yes,
values
sir.
will be determined by the values of x of n at that point, right? So
Yes, sir.
what this del of, okay, I should, okay, we taking, we are taking example of this one, right? X of 0 is 1,
1. Yes, sir.
right? So
Yes.
x of 0 del of n would be 1 at n equals to 0, right?
Yes, sir.
So the dependence of n doesn't fade away, right? It still is there. So that
Okay,
was
sir.
my point, right? Similarly, what will happen for this is del of n plus 2, right? So this would be 0 for all n except n equals to minus 2. And what would be the value at x equals to minus 2? The value that x takes at minus 2.
Okay, sir.
I hope this makes sense that this is not a number but a sequence x of n. Is
Okay,
that
sir.
clear?
Okay, sir.
Okay. Now let's go back to this. Okay. So I'm interested in finding, an expression for y of n, right? I know that this y of n, let me make this. So this is x of n sequence. This is the system S, and I get the sequence y of n, right? Now, y of n is actually this output of this system, right? So when S acts on x of n, we get y of n. Is this clear?
Yes, sir.
Okay. Now, what I did in the second step is I just replaced this x of n by this summation. So this step should also be clear, right?
Yes, sir.
Fine. So now what I'll claim is, see, this is an LTI system, right? I'm trying to develop a convolution sum formula for this linear time invariant system. So it should follow two properties, right? What are the two properties that a linear system should follow? The
Sir,
superposition
superposition,
and
homogeneous.
homogeneity, right? So what does superposition mean?
Sir, superposition when,
Hmm.
sir,
Please continue.
for two inputs we get two outputs,
Okay.
and when we put the linear combination of these two inputs as the system input, the output
Hmm.
should be the linear combination of the outputs when the inputs were separately given to the system, sir.
Correct, correct. That is precisely what superposition means. What about homogeneity? You answered this right. Superposition case. What about this homogeneous? See, homogeneous would mean, say, suppose I have a system S, I give output X, I was getting output Y. Now, if I give output A times X of X, where this A is a constant, I should get this A here as well. Okay, that is
Okay.
precisely what homogeneity means. So,
Yes.
so can I replace this by this? Can you see why this readily follows because of superposition?
Yes, sir. Yes, sir.
This is technically, if I take your example, this is S of x1 plus x2, and you are getting y1 plus y2, right?
Yes, sir.
So this one is fine. What about this? Now I'm taking this x of I, which is a constant, right? X of I
Yes.
is a constant,
Yes.
and I'm taking this out of this system S, because for system S, this x of I would be a mere constant, right? So the fact that I'm able to write this from this is courtesy of this homogeneous property, right?
Yes, sir.
Okay. So given the system is linear, we were able to so far obtain this y of n as the summation I varies from minus infinity to infinity, x of I, s of del of n minus I. Now what about this? Can you describe what this means physically? I'll help you out. This means
Sir,
system
see,
acting on x of n. What is the output of x of n? What about this?
sir, its value will be one for different integers.
Okay, what you are trying to say is maybe
It will
describing this del of n minus I. See, I'll What I'm asking is about this system acting on this. This is basically the output of the system when shifted versions of unit step sequences are given. Would you agree with that sentence?
Okay, sir.
Okay. So what I'll do is I'll denote that by h of I, such that h of I of n is, did I miss out? This is the output to del of n minus I, right? I'll denote h this by this hi of n, such that this is when system acts on this del of n minus I. Okay, so
Okay, sir.
this is notation. Okay, so this would denote the response of this linear system to the shifted unit impulses. So del of n minus I is hi of k. If the linear system is also time invariant, then these responses to the time shifted unit impulses are all time shifted versions of h0 of n. So del, wow, see, I'll first tell you what this h0 of n is. This is the output of the system when the input is,
Sir, del of n minus 1 I.
and I would be 0, right? Because
Okay, sir.
hi of n.
H0.
So this would
Yes.
be precisely del of 0. So
Okay,
when
sir.
I uh, provide del of 0 as the input to the system, I get this h0 of n, right?
Okay,
So
sir.
what about this? If I provide, sorry, that would have been, sorry, this would not have been the output corresponding to del of 0. My bad. It would be del of n, right? It's del of n minus I, right?
Okay,
When
sir.
I would be 0, that would be del of n minus I would be n minus 0, that is del of n, right? This signal is not time shifted. Okay, coming back. So time invariant, the fact that this system is time invariant, I can write this hk of n. What is hk of n? This is the
Output of the system.
output of the
Correct.
system in which this delta sequence is shifted by k,
Okay, sir.
right? I can write that as if it was h0 of n, n is not working, as if it was h0 of n, but time shifted by k. The fact that I can write this is because of this time invariant property of LTI system. Fine.
Yes, sir.
So for notation convenience, what we'll do is we said that this h0 of n was the output corresponding to del of n, right? We'll drop this 0. Okay, we'll write this as h of n such that this is unit impulse response. So now since s is time invariant, for each I we have, see, we were right. So basically we needed to find an expression for s of del of n minus I, right? So then, right, I needed an expression for this. The fact that this is time invariant allowed me to write this hk of n as this. So then I can write this s of del of n minus I by h of n minus I, right?
Okay, sir.
Then I substitute this h of n minus I into this equation. I'll get this. the well-known convolution sum, right, in discrete case. So y of n is summation I varies from minus infinity to infinity x of I h of n minus I, right? So
Okay.
you also denote this by this x of n convolution h of n, right? They both mean the same. This is what this convolution sum is actually. Okay, so given an LTI system, let me see. Okay, so as I said, we developed motivation for this convolution sum in discrete time case. So now we'll draw a parallel case, and I hope we'll get the motivation for this continuous time case. Basically, what is happening is this summation is becoming integral, right?
Integration.
Yeah,
Yes,
this
sir.
summation operation is changing into integration operation for the continuous time case. So this is clear, right? So this is the convolution integral and this is the convolution sum for continuous and discrete time cases respectively. So now let's talk about the types of LTI systems. Okay, so we have LTI systems with and without memory. And a system is memoryless if its output at any time depends on the value of the input at that time. So the output should not depend on the value of the input before and after that particular time instant, right? Suppose I'm interested in finding y of 3. What should it depend on?
Sir, the input at time 3.
Yeah, so x of 3. It should not depend on future instances of time or past instances of time. Okay,
Yes, sir.
so for discrete time cases, h of n is equals to 0 for n not equals to 0. Can you see why?
If n is equal to 0 and for n not equal to 0. Yes, sir. Because del is 0 for n not equal to 0.
Yeah, see, this x of k, this cannot take any value. This can only take value n,
Yes, sir.
isn't it, right? So when you replace this k by n, this is basically h of 0. Okay,
Yes,
so
sir.
this is 0 throughout except for the case when you are having this h of 0, right? Because for that this k is n. So since that is the case, uh, we are having this h of n such that this occurs only at n equals to 0. This would remind you of this definition of what should I say, this unit steps, sorry, unit, what we call this delta, right? Del of n,
Impulse function.
impulse, yeah, unit impulse, del of n. But uh, we'll use this k because we are not sure about the magnitude of this h of n at x equals to 0, sorry, n equals to 0. So we can write h of n as k times del of n. And can you see why this k would be h of 0? See, what I said was when this k is n, since I can only have x of n if I'm interested in y of n. So I'll only have h of 0, right? I'll have this factor, right? So then I said this h of n would be k times del of n, right? I know that this my h of n is actually h of 0, right? Since I replace this h of n by k del of n, then this has to be the value that this h of 0 takes. I hope it is clear.
Okay, sir.
Okay, moving forward, we are fine with this. So now for continuous time LTI systems, we'll do analogous versions, right? We said h of n is equals to 0 for discrete time case. We'll say h of t is equals to 0 for continuous time case for t not equal to 0. And likewise, we'll say that this impulse response would be given by k times del of t, where this k is h of 0, a constant. So this is fine. So yeah, now if this k is 1, this particular k, can we write x of n as x of n times del of n and x of t as x of t times del of t? Can I do that?
Yes, sir.
Okay, wait, what I'm saying is, see, y of n was x of n h of 0, right? And now since uh, since I can write these h of n and h of t as k times L of n and k times L of t, I'm saying that this convolution sum and integral would become this when k is equals to 1. You can check that out yourselves as well. So now invertible LTI systems. Okay. When is LTI system invertible? If if it has an inverse, right? Given a system, it is invertible if there exists an inverse system h1 of t such that the resulting output is again back this input. Okay,
Okay, sir.
so what should be the overall impulse response of such a system? It should be delta of t, right? Because we know if a system has impulse response delta of t, and whatever you feed the system, you'll get back the same. Okay, so
Okay.
we have following condition on the impulse response of the inverse LTI system. What is the condition? That the see when the systems are cascaded, their impulse response are convoluted, right? So h of t times convolution with this h1 of t. This is convolution operation. Okay, h1 of t is delta of t. So similarly, we'll write for discrete time case. We have h of n convolution h1 of n, that is delta of n. Okay, now let's take an example to understand this. Consider LTI system that is given below. Okay, and the question is it invertible? What is the impulse response of this system?
Sir, it is a time shifted version, sir.
Yeah, it is time shifted version. So what should be impulse response?
Sir, del T minus T naught.
Should be del of t minus t naught, right? So
Yes.
this is the impulse response of this system. So what I can do is, so yeah, this is the equation that we are aware of, that y of t is given by the convolution of x of t times h of t, right? This is basically that. Here y of t is this, x of t is this, and this is my impulse response. Now for invertible systems, we need h1 of t, right? Such that we'll cascade that h1 of t and get back x of t, right? That is what was asked in the question as well, right? Is it invertible? So consider following system, right? Uh, okay, can you guess what should be the impulse response of this next sig next system such that the resulting impulse response is such that we get x of t back.
So it should also be a time shifted uh,
Yes, but time
impulse function.
shifted in the other direction, right?
Yes, sir, yes,
This
sir.
was
Advanced.
delayed, that should be advanced, right? So
Yes, sir.
this is del of t plus t naught. So when x of t is fed to this system, we get x of t plus t naught. Okay. So now consider the whole picture. X of t comes, it encounters this h of t impulse response system. We get x of t minus t naught. Okay. Then it's fed to h1 of t, right? The inverse LTI system. What does this inverse LTI system do? It advances the signal by t naught. The overall, uh, I mean, overall this time shift would be zero, right? Because this
Yes.
minus t naught shift and plus t naught shift cancel each other. We are left with x of t. So yeah, this is what it means mathematically in terms of impulse response. We get back this del of t. Uh, it's an exercise for you all. You can try this out. This del of t minus t naught, convolution del of t plus t naught is del of t back. I mean, can you see why this and this is same? Right? This is basically a cascaded system, right? You
Okay,
know,
sir.
for cascaded systems, we take the convolution of the impulse response of the two systems. So for this one, the impulse response was del of t minus t naught. And for this system, the impulse response was del of t plus t naught. So try it out mathematically and see if you get this answer.
Okay, sir.
This is the exercise part. Now, causal LTI systems. Okay. LTI system is causal when the output of causal system depends, sorry, I messed up. Should be when the output of the system depends only on the present and past. It depends only on the present and past values of the input to the system. So the condition is that the output of the system should not depend on future values of the input. Right? Suppose we have again this y of 3. It should not depend on this x of 4, right? Because x of 4 would be a future instant of time. It should either depend on x of 3 or x of 2 and so on. So for discrete time case, y of n must not depend on x of k for k greater than n. Is this fine?
Okay, sir.
So yeah, these are my convolution sum and integrals. Let me see what I can do. So all the coefficients h of n minus k that multiply the values of x of k for k greater than n must be 0. Why? Because y of n should not depend on those x of k's, right? So x of k would be 0 when k is greater than n. Okay, so this x of k would be 0 if k is greater than n. So k is greater than n. Let's take a value. Suppose k is n plus 1, right? N plus 1 is greater than n. Similarly, n plus 2, n plus 3, and so on. So these should these be 0 or should these exist?
Sir, the value of input function at this point of time should be 0.
Yeah, if this is 0, then we won't have this, right? So the idea is the coefficients of these h of n minus k that multiply the values of x of k must be 0. See, it is quite possible that x of n would exist at these points. So the
Yes.
only way to make them 0 would be to make these coefficients 0, right? Because impulse response, you can think of it as a control, right? You have control over this, the response of the system, but you don't have control over the input, okay?
Okay, sir.
So we'll play with this and see what condition should this impulse response satisfy. So now for n plus 1, for k equal to n plus 1, what is this?
K is equal to n. Sir, 1. 1.
Would it be 1 or minus 1?
K is equal to n. Yes, sir, minus 1. Minus 1.
Right? It would be minus 1. So this would be minus 1. Similarly, for n plus 2, you'll see that this would be h of minus 2. Right?
Yes,
So
sir.
this is the pattern. It would be h of minus 1, h of minus 2, h of minus 3, and so on. These all should be, these all should be,
0, sir.
yeah, these all should be 0. So h of n should be 0 for n less than 0, right? For minus 1, minus 2, minus 3, n is less than 0. So let's take an example. Suppose y of n is 2 times x of n plus 3. Okay. Suppose y of n is given by this. Will this be causal?
No, sir.
Why it won't be causal?
Sir, if x of n is 0,
Yeah.
then also there is an output that is
But
3.
but we did not impose any such condition, right? We did not say that say x of, if we apply, so suppose a 0 input, the system should give a non-zero output, right? The only condition that we imposed on the system was the output of the system should depend on the present and past values. In this case, when you'll compute y of 0, it will depend on x of 0,
Yes.
right?
Okay.
Because n is same.
Yes,
So
sir.
it
I
is
confused it with
depending,
that memory release system.
yeah. So it will depend only on the present instances of time,
Yes, sir.
right?
Yes, sir.
When y of 1 would be there, it would depend only on x of 1. It won't depend upon any other value of x of n
Okay, sir.
other than 1. Okay, so you can see uh, in the same way as we came up with this equation of impulse response for discrete time system h of n, you can come up with this, right? For discrete time case, it was h of n is equals to 0 for n less than 0. Similarly, for continuous time case, you'll have h of t would be 0 for t less than 0. Okay, this part is clear. Okay, one more thing. Since we have this particular thing, right? We saw this just now. So won't our summation and integral limits change, right?
Yes, sir. It may.
Okay, then why should it change from 0 to infinity? This is my question, if you agree with this.
Sir, for the values of k lower than 0,
For
mm,
values of k lower than 0.
the, the सर सर क्या बोले इसको सर जो भी
Mhm.
फंक्शन की वैल्यूज हैं सब जीरो हो रही हैं तो आप उसको कितना बार भी जोड़िए कोई फायदा नहीं है
Okay, function. is not getting 0, right? The only statement that we made was the coefficients can be 0, right? Okay, I'm with you if you say this is 0, right? See, let me get to the point straight away. The idea is x of n convolution h of n is same as h of n convolution
X of n.
x of n. Okay,
Yes, sir.
and if that is the case, can you write this summation as k equal to, why is it so thick? Can I reduce the thickness? Okay, k minus infinity to infinity h of k, right? X of n minus k. Why I can write that? Because these are commutative.
Okay, sir.
Okay. Now, if that is the case, then I'll use this result that negative h of minus 1, h of minus 2, h of minus 3, they all are 0. So in other words, when k is less than 0, this summation, it won't contribute to this summation. I hope this is clear, right?
Yes, sir.
Hmm. So that is why I can write this. I have changed this minus infinity to 0, because prior to that the summation would be 0. Why? Because h of k would be 0. Similar
Yes,
is the case with this continuous time case. Okay,
sir.
I'm
Okay.
replacing
Yes.
this minus infinity by 0 by using making use of that commutative property of this convolution
Okay, sir.
integral or sum. Now coming to the stable LTI systems. Okay, LTI system is stable if every bounded input produces a bounded output. Okay, now in order to determine the conditions under which this LTI system would be stable, we can consider an input x of n, right? That is bounded in magnitude. Suppose we have x of n input and it is bounded in magnitude by this b, such that this magnitude of x of n is less than b for all n. Okay, and this b is finite. So, okay, this is less than b for all n. Suppose LDI system is having unit impulse response h of n, then I can write this. Why?
So the above properties, sir.
Yeah,
Convolution.
I am just used convolution sum. I have replaced this y of n by the convolution sum. Then it follows that this holds good. Can you see why? If this holds good, then this should hold good. Which fact have I used? Okay, I've used the fact that sum of set of numbers, the magnitude of that is always less than sum of magnitude of the numbers. Is this clear or should I show it via example? Let
Sir,
me take an
please explain.
example. Should I take an example?
Yes, sir. Yes, sir. Please.
Okay. See, suppose you have the following 2 minus 3 plus 1. This. Okay.
Okay, sir.
What is this? This is 2 plus 1 minus 3. That is 0, right? Now, it's always less or equal to the individual sum of magnitudes of those numbers. For example, 2 plus mod of minus 3 plus mod of 1. That would be 2 plus 3 plus 1, right? Which is 6. So this is a case, a simple case where this holds good. I hope
Okay, sir.
this is clear why this makes sense. So I have used this particular fact in writing this inequality. So this is fine, right? So I can write this y of n as y of n is less or equal to. B summation k varies from minus infinity to infinity, modulus of h of k for all n. Why? Because see, x of n is less than b for all n. So x of n minus k is less than b for all k and n's, right? If a particular signal is less than n, the time shifted versions of that particular signal would also be less than that bounded value, isn't it?
Yes, sir.
So I can then say that this is less than b. So the magnitude of y, that would be less or equal to, I'll take this b out of this sum. I'll write this b summation k varies from minus infinity to infinity h of k, modulus of h of k for all n. In fact, this is, I hope you can see, this quantity is larger than this quantity, isn't it? In other words, this is smaller. Why? Because b is smaller than this. Sorry, b is greater than this. Sorry, this is larger. Sorry for the confusion. So I'm saying is this particular quantity is greater than this because b is greater than the magnitude of the signal. So I can readily use this inequality, greater or equal to inequality. So if I can do that, what will be the sufficient condition? Sufficient condition would be that the summation, see, if this is to be bounded, b, we know that b is fine, right? So this summation k varies from minus infinity to plus infinity modulus of h of k, that should be bounded, right? In other words, that should be less than infinity. And this is in fact the sufficient condition for a system to be stable. Only then y of n is bounded in magnitude and hence the system is stable. So with that, let's now start doing problems. Problems won't take time. That's why I spend more time in these definitions. So try this out. Which of the following system defined by their impulse response is causal and stable? I can maybe help you out. What is u of 3 minus t? Right, u of 3 minus t would be this. Agreed?
Okay, sir.
Similarly, what about u of t plus 3? See, this is reversal and then an advance. See, I can write this as following. This I can write as u of minus times 3 minus 3. So this would be a reversal and a delay. That's why I wrote this as u of 3 minus t. And again, a simple check would be at t equals to 3, this should be 0, right? And that is indeed the case. At t equals to 3, this is 0. Now what about this u of t plus 3?
Sir, it is advanced signal, sir. Same
It
unit.
is advanced signal. Okay. and we are not having this time reversal and anything. So let me make that SST. I don't know what happened. This is u of t plus 3. What about u of t minus 2?
So unit step function with
Hmm?
uh, delayed 2 units.
Delayed 2 units. So it should be something like this, right? What about the last one? U of minus t minus 1.
So unit step function advanced
Mm-hmm.
1 time unit and then reversed in the
Okay.
uh, time axis.
So basically you are saying this particular thing. And it would be this. Agreed? So which one should be causal? We'll come to the stability part later. First, which one should be causal? Again, for all these, we have this e to the power minus 60, right? E to the power minus 60 would be 1 at t equals to 0, right? It would be something like this. I'll not draw this to scale, but the trend should be this. It's somewhat this. Do you agree?
Yes, sir.
Okay, so which one should be causal? Now, the what would be the signal? Signal is basically multiplication of these two. Okay,
Yes.
so you'll have the whole signal for
Sir,
case
here
A.
the input is unbounded, sir.
Okay, firstly, let me draw all of these. So just correct me if I'm wrong. Right, it would be this. And likewise, okay. Now comment on the causality. Yes, you are right. This is not stable. Sorry for
Okay.
the confusion. Okay. So what about the causality?
Sir, I believe all the systems are causal, sir.
How do we determine the systems are causal?
Sir, the system should not be dependent on future inputs.
System should not depend on the future instance of time. There was also one more result that we derived, right? For causal systems, we had derived this particular thing, right? If we talk about the impulse responses, they should be 0 for t less than 0, right? And if you'll see for all these theory cases, only this one is satisfying that, right?
Okay, sir.
So which particular system is causal? This is causal, right? This would
Third
be
one.
causal. This would be non-causal. This would be non-causal. This would be non-causal. And if you'll see for this particular causal system, why would this be stable? Because as you rightly pointed out, in this range, it's not diverging, right? Yeah, there was an issue for this. Actually, I was focusing on this one. That's why I got confused. See, here the input is bounded, right?
Yes, sir.
Here, for this case, it's not bounded. For this one, it is bounded. Here again, it's not bounded, right?
Yes,
So
sir.
this is causal and stable. Which option is right then?
Third option.
Third option is right. Okay, I guess I did not need this. Okay, now the second question. Which of the following systems defined by their impulse response is causal and unstable? Firstly, you'll need to plot all of them, right? Let's try to plot. Let me take a separate page. This, okay, the first one is e to the power minus 70 u of 2 minus t, right? So this would be, this is u of 2 minus t. So this would be, right? This is that unit step signal u of 2 minus t. Agreed?
No, sir. Sir, this signal will be shifted towards the left, sir. 2 units.
See, u of, it is similar to this case, right?
Sir, there you have written u 3 minus t in the form of u minus bracket t plus 3 and t minus 3. Then we have similarly in this case if we write e- sir
Okay,
u.
okay. I'll tell you one thing. A basic sanity check that we always perform is, where is this whole argument zero, right? That
Yes,
would be the turning point, right?
yes,
That
sir.
would be t equal to 2, t
Yes,
equal to
sir.
2, right?
Yes, sir.
So do you agree with this?
Okay, sir. Then this is
Fine, then this is fine. So now what about this e to the power minus 70? Let's draw that e to the power minus 70. I'll only draw that in this unit step region, okay? So this what exists throughout, something like this. Okay, so comment on the causality of this system. What is this? This is h of t, right?
yes, sir.
You are given h of t in the question. So is this causal?
No, sir.
This is not causal, right? So this option A is not correct. We'll move on to the second option. Note we need to find an unstable and a causal system, right? In the question first we had a causal and a stable. Now we need to find a causal and an unstable system. What about this?
Sir, it is also non-causal.
It will be a non-causal. Why? Because in fact the plot of this would be something. Agreed? Why? Because for t less than 0, this would be an exponential function, a positive exponential function. And for t Greater than 0, this would be a negative exponential function, hence this kind of behavior. So since we are having this portion, this is non-causal as you rightly pointed out. Okay, moving on to this one, the third one, t e to the power minus t u of t. So this time it's fine, right? This is u of t. T u of t would be, okay, agreed. This is our usual u of t.
Yes, sir.
Now it is t e to the power minus t. T e to the power minus t. See, when t is less than 0, this linear t term would dominate. Okay, and then I know it exists in this region. Now what will happen is, and then as t becomes greater than 0, this exponential would dominate. This, since this is a negative exponential, would be something like this. Do you agree?
Okay, sir.
One thing that we are sure is there won't be any signal for t less than 0. Why? Because this is multiplied by u
Unit
of
step.
t. Yeah, unit step. So is this a causal system?
Yes, sir.
Is it a stable system?
It can be, sir.
It is stable, right? See, it is, see, even if we have a very large value of t, it is anyways converging, right? It's not diverging. So this would be stable.
Okay, sir.
Okay, this would be stable, and anyway, we are not considering this part. So this is causal and stable. What about the last one? No, this would also be causal. Why? Because we have this u of t.
Unit step. Yes, sir.
Yeah, unit step. Now the only thing to uh, find out is how would be the behavior of the function. Let's find out the behavior. E to the power minus t. E to the power minus t would be, I'll draw both of them. This is your e to the power minus t. Agreed. Now what about this? This is an exponential, right?
Yes, sir.
E to the power t minus 1. It would be 1 at t equals to 1.
Yes, sir.
So let's draw that. I'll draw this by green color. So this would be, I removed this part because since it's anyways multiplied by a unit step signal, right? One more
Yes, sir.
thing, you have this exponential behavior. I mean, e to the power positive exponential, but since there is a negative sign, so we'll flip it,
Yes, sir. Along the time axis.
yeah, along the time axis. So what we'll get is,
Mirror image of e to the power x.
yeah, e to the power x mirror image, something like this, right?
Yes, sir.
So then we'll need to add both. Okay,
Mm.
when you'll add both, see this one is converging. Can readily see this. And this one is diverging.
Yes, sir.
It's,
And this will dominate as t passes.
yeah, this will start dominating and hence the system is
Unstable.
unstable, and causality was already taken care of by u of t, right?
Yes.
So this is, as you said, this is causal plus stable. Okay, so this one is done. Let's move on to the third part. Which of the following system is causal?
Yes.
Will the first one be causal?
So how can we say that we don't know what is the form of xt? It is
Okay,
entirely
okay, okay.
minus
This
it.
system should be a non-causal
Causal.
system, right? Let it be, we corrected it. So this would be a, use a different pen, non-causal system. Okay,
Yes.
so now coming to the part B, right? Part B is x squared of t plus x of t minus 3. What about this?
Sir, it is causal, sir.
It is causal. Why? Because output is not depending upon any future instance of time of the input.
Yes. Yes.
So this is causal. This is fine. In fact, I'll write this as causal. What about third part? Y
Sir, it
of
is
t
non-causal.
is, it is
Non-causal.
non-causal. And why it is it non-causal?
Sir, if we put t is equal to 0, then the first part x will depend on take the value of
Hmm.
x3,
Okay,
x4, sir. It is a future input.
yeah, you got the point. So this should be non-causal. And similarly, the last one would also be
Non-causal.
non-causal, right? Because it would depend on the future value of the input. So
Yes.
which option is correct? Would be
Second.
option B, yeah. So let's move ahead. Now, for the system in figure 1, you need to take the correct answer. Okay, I'll wait for 3 minutes and then start doing it myself. Attempt this one. So you need to comment on two things, right? The memory, whether the system has a memory, or the causality. Both we discussed today, right?
Yes.
So try to solve this one. For causality,
Yes, sir. What?
we'll just need to look at this expression, right? Y of t is x of t times cos of omega 1t. Will this play a role in determining causality? Cos of omega 1t. Input is this, right? Consider this as part of the system. Input is only this part, right? So for causality, you look at this part, right? And since this depends only on the present values of the input x of t and not on the future values, so it is
Causal.
it is causal, right? So one part is clear. It has to be causal. So which option could be correct? Either this or this. Now we need to comment on the memory part. how do we determine if a system is memory or has a memory or the system is memoryless? How do we determine that?
So for zero input, it should give zero output.
For zero input, it should see, in other words, it should depend only on the present value of the input, right? It should not
Yes.
depend on the past or future values of input, only
Yes.
on the present value. And that is the case over here, right?
Yes, sir.
It is only depending on the present. So this system is
Memory.
memoryless, right? Memoryless. It's not
Yes.
having memory.
Yeah.
So the system is memoryless and is causal. Option C. Is this clear?
Yes, sir.
Okay, we'll move ahead now. Okay. For the same figure, you need to comment on the linearity and time variancy or invariancy. Okay. Okay. Firstly, you know how to find if a system is linear, right? You can use the superposition and homogeneity properties. Okay. Try to do that. Take two inputs, x1 of t and x2 of t, and see if the linearity property is satisfied. That is how you will proceed for this question 5. And then we'll move on to the time variancy part. I should, I guess, make this one. Okay, now you have it on the same page.
So the system is linear.
The system is linear. Okay. Uh, you took the two inputs, right? And computed the individual outputs and then found out the output corresponding to the sum of these outputs, right? Sum of these
Yes.
inputs. Okay. And you can see why that would be true for any number of inputs, right? Because linearity is not restricted to two number of inputs. You are right. The system is linear. Now, uh, what about this? Is it time variant or time invariant? First of all, what is time invariant system?
Sir, if if we change the sir, point of application of input in time,
Mhm.
same, the output should also change according to it.
Output should also take. See, since in this one we have a time dependent part, right? Cos of omega 1 t, isn't it? We have this time dependent part in the output. X of t was your input, right?
Yes, sir.
Since we have this time dependent part, so this would be a time invariant or time variant. Is it varying with time or is it time invariant?
It will vary with time.
So it is time variant, right? So option A should be correct, right? You said it is linear, right? And then
Yes,
we
sir.
came to conclusion that it is time variant as well. So we'll move ahead. Okay. So the next question is okay. This is again for the same. I'll paste it here as well. Okay. For the same system, we need to now comment on the LTI, whether the system is LTI. What does LTI stand for? Linear time
Time,
invariant.
time.
Firstly, that part is right away clear, right? We came
Yes.
to
Got
conclusion that This is time variant system. But the other part is still left, right? Is this what about the stability? Is it bounded input, bounded output stable?
Yes, sir.
Will it be bounded input, bounded output stable?
Yes, sir. It will be stable, sir.
Fine.
Because the maximum
Why?
value of cos will go to 1, sir.
Yeah, because cos is a bounded function, right? So the output of this y of t, it will not diverge, right? And it will remain bounded in amplitude. Okay, so this is bounded input, bounded output stable. So which option is correct?
So third, sir. The system is
Third
not
one,
LTI, however, it is BBO stable.
stable, stable. Fine, correct. Now we'll determine the transfer function. I'm sure this one would also have been discussed, right? Since this was a straightforward, that's why I did not cover in the recap part of this session. So you need to compute the transfer function, okay, in the frequency domain of the system. What is transfer function? The ratio of that output voltage to the input voltage. So since you need to compute it in frequency domain, what will you do?
So it's frequency transform.
Yeah, you will use a frequency transform. In other words, you will write down these impedances in that form. For R,
Yes, sir.
it is same, right? R
Yes, sir.
remains as such. What about
Yes, sir.
C?
Sir, 1 by j omega c,
1 by j omega C. And what about L?
j omega l.
Yeah. Likewise, we'll have following thing. Mm, This y of t would be y of omega, right? And this x of t would be x of omega. In
Yes, sir.
other words, we need to compute this. This is nothing but a voltage divider, right?
Yes, sir.
Yeah, compute this one.
So the last option, sir.
The last option, option D.
Yes, sir.
Okay, let me see. I have not yet solved it. X of omega. So what would be this y of omega by x of omega? Just help me out if I make a mistake. Okay, we'll have 1 plus r j omega c, right? Plus j square is minus 1. So this would be minus 1. Would be omega square LC, right? Minus omega square LC. Yeah, you're right. Last option is correct, right?
Yes, sir.
Hmm. That was easy question. Now what about this? We need this. Okay, so I'll take a screenshot again. Okay, this is your figure 2 and you need to determine the type of filter, right, for the system shown in figure 2. Hint is that you already found out the transfer function, right? You can use this.
Sir, high pass filter.
Is it a high pass filter? Let's see why Let me copy this one, or I may just write it out. Y of omega by x of omega. What was the transfer function? Minus omega square LC, all divided by 1 plus RJ omega C minus omega square LC. Right, this was the transfer function. Now, for lower frequencies, we'll put that what happens to this transfer function in the limit omega tends to 0. Right, let this be h of omega. What happens to h of omega?
Omega will tend to 0.
This would tend to 0, right? See, this one would cancel, this one would cancel, this one would cancel. This would be 0 by 1, which is not indeterminate and hence 0. Now, what about the other limit? So this filter would allow low frequencies to pass. Will it? It won't allow, right? Because this transfer function is 0 for lower frequencies. So it won't allow low frequencies to pass. What about the other side? Limit omega tends to, I'll take the other case when limit omega tends to infinity. Uh, I guess I'll need to use L'Hopital's rule. Let me use a separate page. For this limit omega tends to infinity, h of omega. Okay, that is, I'll use L'Hopital's rule. Why should I use L'Hopital's rule?
To avoid indeterminate form.
Yeah, and which indeterminate form were we encountering in this case?
Yes, sir, infinity by infinity.
Yeah, infinity by infinity. So once I use that, I'll get minus 2 omega LC, all divided by differentiation of 1 is 0. For this, it would be RJC. This would be minus 2 omega LC, right?
Yes, sir.
And again, if I use omega equal to infinity directly, I'll again get infinity by infinity form, right?
Yes,
So I'll again uh, differentiate numerator and denominator and use L'Hopital's rule. So it would be 8, might lead to confusion. This would be minus 12C all divided by, this is again 0, minus 2 LC. What is that?
1.
That is 1, right? So in the limit, when omega tends to infinity, this transfer function goes to 1, right?
Yes.
So clearly it is an high pass filter, as you pointed out. High pass filter. So option B should be correct, right? Now the last question. You need to determine the order of the filter for the system shown in the figure. Okay, let me copy this one.
सर इसके बारे में आइडिया नहीं है सर, बता दीजिए।
Okay. So the fact that, see, the order of the system, the one simple way to determine is that by looking at the number of energy storage elements, right?
ओके सर।
And how many energy storage do we have?
टू सर।
Two, right? Capacitor and an inductor. So this is a second
सेकंड।
order. Okay. The other way to do is to look at the poles, number of poles in the transfer function, right? And if you look at that, this is a second order polynomial, right, in the denominator. So it will have two roots, right? So
यस।
correspondingly will have two poles.
ओके
So you
सर।
can use either of the approach. You will come to the conclusion that it is a second
सेकंड
order.
ऑर्डर।
Yeah. So yeah, that was all for today's session. If you have any doubts whatsoever, you can ask.
सर ये
Hmm.
डेस्मोस को यूज करने के बारे में पूछना था सर।
Sure,
उसमें ये
sure.
यूनिट फंक्शन और एक्सपोनेंशियल फंक्शन कैसे बनाएंगे सर?
Unit step or exponential? Exponential, we can easily make exponential function. Unit step, a heavy side step function भी बोलते हैं. I'll check. Wait. I can check that and let you know.
सर खुद से चेक करने की मदद
Okay,
करेगा
okay.
डेस्मोस?
Yes. And you can use Desmos for many questions, especially in signal and systems. Desmos. Okay. Heavy side step function in Desmos. Okay. I'll write something in chat. Uh, just try this one out. Okay. So
ओके सर।
basically unit step function जो है उसको हम heavy side step function भी बोलते हैं. Okay.
ठीक।
I tried to paste लेकिन ये paste नहीं हो रहा है. Wait, I'll share my screen instead. Okay. I'll share my screen so that. Are you able to see this?
नो सर, योर फेस इज गॉन बिग सर।
Okay. I understand. What about now?
यस सर। यस सर।
Now it's fine. See, this is how you can do it. H of t is equals to, for t less than 0, it is 0. So this is basically a conditional assignment. In the same way how unit step is defined, I basically wrote this thing, right? See, suppose now you have a step case. What will you do? It is, if I use this, no, my bad. Okay, let's think over it. Hmm. So unit step तो implement हो गया, right? Unit step implement हो गया. अब वो है कि if you'll have those cases,
शिफ्टिंग एंड स्लीपिंग।
हाँ shifted वाले अगर cases आ जाएंगे. So this one is also implemented, right? Which one? U of minus t, right? What I did for U of minus t, I just replace these t by minus t's. Now what about time shifted versions? So if I use t minus 1 and t minus 1, then it is implemented, right?
ओके सर।
And likewise, you can play with this function.
ओके सर।
Okay, suppose this is h of t, and now suppose I have another function a of t, which is e to the power 2t, right?
सर
And now
मॉडलेस
I'll
ले
def modulus वो भी
ई
कर
टू
सकते
पावर
हैं,
mod t लीजिए तो सर.
e to the power mod t ले लेते हैं. Fine.
नहीं सर.
Now what I'll do is I'll compute c, function c, which would be this h of t.
कॉन्वोल्यूशन.
नहीं, मैं मल्टीप्लीकेशन करूंगा, ठीक है.
ओके सर,
I'll perform a
मल्टीप्लिकेशन.
multiplication. Convolution ऑपरेशन शायद ऐसे रेडीली नहीं हो जाएगा, इसलिए मल्टीप्लीकेशन a of t. ओके, एक्चुअली कलर सेम आ गया, अदरवाइज दिस इज एक्चुअली
रेड.
इम्प्लीमेंटेड. कहाँ पे हो जाएगा? ओके, इसका कलर ऑरेंज कर दिया. डन. सो ये जो ऑरेंज फंक्शन है, दिस इज द प्रोडक्ट ऑफ दीज टू, राइट? यहाँ पे एक स्टेप है, शिफ्टेड स्टेप, और एक एक्सपोनेंशियल है.
यस
ठीक है.
सर. सर ई का
हाँ,
पावर लगाने के लिए क्या क्या कमांड दिए सर?
यहाँ ओके ओके, ई का पावर, राइट. देखो ये ई है. आई यूज शिफ्ट प्लस सिक्स. शिफ्ट और सिक्स अगर कीबोर्ड पे दबाओगे तो ये खुद ही
यस.
ऊपर चला जाएगा, ठीक है? ये ट्राई करना. तो
ठीक है सर.
मैं लिख देता हूँ चैट में, फॉर पावर, नहीं, फॉर एक्सपोनेंट शिफ्ट. बिकॉज अगर देखोगे कीबोर्ड पे सिक्स में होता है ना ऊपर वो एक्सपोनेंट का साइन.
हाँ सर, हाँ सर है.
हाँ हाँ, इसी वजह से. जो शिफ्ट वाला होता है, शिफ्ट के बाद जो भी दबाएंगे ऊपर वाले होते हैं, तो उस वजह से किसी तरह वो साइन चाहिए. अगर किसी कीबोर्ड में डिफरेंट भी होता तो मैं शिफ्ट प्लस वो वाला बटन दबा देता. यूजुअली क्या होता है, या तो शिफ्ट प्लस वो बटन होगा या कंट्रोल प्लस. डेस्मॉस में शिफ्ट प्लस वो चलता है, तो यही याद रख देना.
ठीक है सर.
कुछ और? एनी एल्स क्वेश्चन, कुछ भी?
नहीं सर, ठीक है सर अभी.
ओके, fine, I guess let's end the today's session. Thanks, Neeraj.
ओके सर. गुड नाइट सर.
Good night.